Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I hope that you all have a very fine week so far. We want to thank you very much for joining in on this webinar today on how to determine your worst case scenario for surge analysis. And I have another very special guest with me to present again today, Mr. Dylan Whitty. He is the project manager of AFT's sister company, Purple Mountain Technology Group. And Purple Mountain Technology Group is an expert in hydraulic analysis, and they provide consulting services. And so if you ever need any help with flow modeling or Waterhammer analysis, be sure to contact Purple Mountain or Dylan Whitty at pmtechgroup.com, and he'll be glad to help you. Anyway, we're going to go ahead and get started and jump into things. This webinar is being recorded. That way, if you want to watch it again later or send the recording around to your colleagues, you'll have the ability to do that. And then also, shortly, the PDF of this presentation will be available here soon in your handouts. And once I get that, I'll drop it in the handouts box and you'll have access to it. And then for those of you who are listening to the recording, if you'd like a copy of the presentation, please email Dylan Whitty at pmtechgroup.com. That's DYLANWITTE at pmtechgroup.com, and he'll be able to send it over to you if you're listening on the recorded version. All right, Dylan, I'm going to go ahead and turn it over to you, and go ahead and take it away.
Okay, good morning, everybody. So, like Ben was saying, I work over here at Purple Mountain, keep everything afloat, and do a ton of surge analysis. And so a lot of what the next hour is going to be is just going to be a lot of shop talk, talking about surge and really what that means. So if you have any interest in this, be sure to email me or give me a call. So both of those data points are on this first slide. So, but without any further ado, let's get to it. Okay, so one of my favorite books of all time is Thorley's Fluid Transients and Pipeline Systems. I think this is pretty much a need to purchase for anybody who's serious, any working engineer who's serious about surge analysis. But one of the best quotes in there is on page 133 of the second edition. With respect to fluid transients, the evaluation of risk is often quite complex and usually requires a significant amount of engineering judgment. This arises for two reasons. First, no two systems are really quite the same, so problems that can occur and the practical steps to overcome them differ from one system to another. Secondly, important items of data that are needed for an analysis are frequently not available at the time the assessments are required and have to be assumed or estimated. Okay, so that's a lot to digest. That really is the core of what it means to be a surge analyst. So what we're going to do today is try to demystify some of the aspects of fluid transients and what makes one scenario worse than another. Okay, so another introduction is your system is unique. There is no one-size-fits-all solution to your surge problems or any surge problem. Everything has to be handled differently. Just because that surge accumulator or that relief valve worked on a different system doesn't mean it's going to work on yours. Okay, and the only way to determine your worst case scenario is to have a deep understanding of fluid transients and your system's function. So hopefully you weren't coming here today just hoping to get a step-by-step bullet list of this is how you determine your worst case scenario. You really have to understand surge transients and fluids in general, the software that you're using, and your system. So some of the core concepts. Wave speed is king. Okay, so wave speed is oftentimes called celerity. We're going to talk about the Joukowsky equation. Oftentimes it's referred to as the textbook worst case. You'll look at some engineering reference manuals that kind of aren't specialized in surge analysis, and they'll say, oh, just do Joukowsky equation, instantaneous Waterhammer equation, you're set. That's the worst pressurized you're ever going to see. Spoiler alert, that isn't the worst case. We're going to talk about when it's right, when it's wrong, pipeline period, communication time. This is a critical aspect of any surge analysis. We're going to talk about the magnitude and rate of change in flow. So that's essentially, think about how high is your initial velocity and how fast do you change it. Those are two separate things, and both of those are very important. And we're going to talk about forces, why they're different than pressure, typical worst case events, and complications to all of this, and some of my final thoughts. Okay, so wave speed is king. You can see it has a crown, that's why it's king. But wave speed determines pretty much all of the core aspects of a surge analysis. Okay, so wave speed determines pipeline period or communication time. That's the time it takes for your wave to go from the point that the surge is initiated to a upstream or sometimes downstream boundary condition, reflect off that, and come back to that same source point. So that's 2 times L over A. So that's length over speed. You're going to get a time associated with that. Okay. It's going to determine your pressure response to a corresponding velocity change. We'll see more of that with the Joukowsky equation. And if we're talking specifically with impulse and other method of characteristics solutions, that's going to determine your pipe sectioning. Okay, so all of those are going to have a dramatic effect on the analysis. And after we said it's the most important thing, it's important to remember that the equations for wave speed are only estimates. They have errors typically in the range of 10 to 15%. And then I define all of the terms for wave speed under there. So you can go through those real quick. A is wave speed. More specific definition is speed at which pressure and flow changes travel in a constrained pipe. So each of your pipes is going to have a different wave speed because each of your pipes might have a different diameter. Each of your pipes might have a different thickness. They might be made out of different materials. So keep that in mind when you're modeling your system, is don't just assume everything's steel. Typically, most modern industrial systems are carbon steel. But some of them have plastic pipes, some of them have cast iron pipe. Those are going to change your wave speed. Okay, so, and this wave speed term kind of lumps together your fluid and your pipe into one term. Okay, so we have the bulk modulus of the fluid, which is essentially, when we're talking about incompressible fluids, we say they have no density change, they have no volume change with increased pressure. That's not entirely true. It works really well for steady state, solving Bernoulli equation, things like that. But for Waterhammer analysis, Waterhammer wouldn't happen if everything was perfectly incompressible. So bulk modulus is essentially a measure of how compressible your fluid is. Density of your fluid, that's obviously important. And then the rest of the terms are essentially about your pipe. There's the constraint coefficient. I would recommend looking into AFT Impulse's help file, or Wiley and Streeter, the good book of fluid transients. This is the book that is referenced in every other book. This is kind of the original source material. They talk about constraint coefficients and all of that and what those mean, what types of systems they work on. That's essentially changes depending on your pipe supports. We're going to talk about Young's modulus for pipe material, pipe diameter, and pipe wall thickness. So all of those matter. A little more in depth on that is by inspecting the equation and kind of just thinking about what happens if this value gets larger or this value gets larger. I mean, larger or smaller. We can see that a larger K or a greater K leads to a higher wave speed. That might be a little bit confusing because K is both in the numerator and the denominator within that square root. But your K over rho is typically far larger than your K over E, because E is typically a very large number. I'm sure there's some weird specific case where that's not the case. There's some exception to that rule, but I haven't ran into it. Here's the confusing part. A greater rho, or density, leads to a lower wave speed. That is true, but you get a greater pressure rise. Because when we're looking at the Joukowsky equation or the instantaneous pressurized equation, which I put here, let's see, let's try the pen. So I put the Joukowsky equation here. You can see that rho is a term in, I'm an artist. You can tell I went to art school, not engineering school. So rho is a term in this equation and this equation. Rho has more impact in the Joukowsky equation than it does in the Waterhammer equation. Okay, because it's not in a square root, it's kind of just by itself. Greater C1 leads to a lower wave speed, which might seem kind of confusing, but it's in the denominator. The larger the denominator terms, or the whole sum of the values of the denominator, the lower your wave speed is. So essentially, higher constraint coefficients are associated with less rigid pipe support structures. You can see a greater E, or Young's modulus, leads to a higher wave speed, because if that value goes up, this entire denominator value goes down. Okay, let's see. Greater diameter leads to a lower wave speed. Essentially, as your pipe diameter gets larger, you're going to have more room for flexibility. As your pipe thickness gets higher, you're going to get a higher wave speed. So all of those kind of come together into this general rule that is, the greater the stiffness and inability to flex, move, or expand of the fluid and pipe taken as a whole, the higher the wave speed. So think about all those things when you're, maybe you don't know what your pipe size is yet. Well, you probably know what your pipe size is. Maybe you don't know the thickness, but you know what the upper maximum of the thickness is. So your worst case is likely going to be your thickest pipe. Maybe you have two differing values for bulk modulus. You have some funky fluid. You've seen two references online. One's engineeringtoolbox.com and the other's some guy's like college project that he just put a PDF online. You don't know which one to use. It's not the greatest reference in the world. You don't feel very confident about it. It's probably a better idea to use the higher value as a conservative estimate. So keep this in mind. That's why I'm going into depth about all this, because sometimes you don't know all of these. So you have to determine, well, which one's worse. This helps you think about that. Okay, let's see. I need to turn off my pen. Normal non-drawing mode. Ooh, there we go. Okay. So the Joukowsky equation 2.0, we're going to talk about this some more. You can look at it in two different terms. There's the change in pressure is related to negative rho A delta V, and delta H is equal to negative A delta V over G, or the gravitational constant on Earth. You can see heads kind of, we get rid of the rho term and add the G term there. So Joukowsky is often referred to as textbook worst case. It's far from the truth. Joukowsky shows that for any given instant velocity change, the instant pressure rise is directly proportional to wave speed and density. Okay, so with few exceptions, systems with higher wave speeds will have a more significant pressure rise or drop. So you can think about that for pump trips. Oftentimes people, when they first get into surge analysis, they're like, oh, that's just what happens when a valve closes. We only know anything about valves. Pumps and other components matter a lot. I'm sure a lot of the attendees here listening know that, but that's something you might have to explain to your clients. Okay. So when it's right, the Joukowsky equation is actually an analytical solution. So it's always right, but that's for an instantaneous change at a single point. What that means though is systems are not single points that experience instantaneous stoppage of flow. So if you're actually modeling a real system, you can't use Joukowsky equation. It's just not going to be right. Okay. So oftentimes when it's wrong at predicting maximum possible pressure rise in a system is in the presence of cavitation or liquid column separation. Fluid cavities, when they form and then collapse again, can collapse at a higher combined velocities than the initial system velocity. So really what that means is when those two velocities meet at that one instant, you can still actually look at the Joukowsky equation to actually look at a single node and a single velocity change to predict what your pressure spike is from cavitation collapse. You have to use a software to be able to do that. You have to put that into impulse, but you can look at the graph values of velocity upstream and velocity downstream at a node where cavitation is forming, and right when it collapses, that velocity change when it collapses is going to correspond pretty dang well with the Joukowsky equation. And then it's also wrong for real system piping arrangements that can lead to multiple interacting and additive pressure waves. So that happens with pipe size changes. When you have a pipe size change, you have partial reflections. Some of the waves going to go upstream, some of the waves going to go downstream. It's going to reflect off other things, and then when they meet again, you can have a higher spike. If you have parallel lines, the pressure wave is going to split through those parallel lines and kind of disrupt this smooth square waveform that the Joukowsky equation or an instant valve closure is associated with. Dead ends will also cause larger pressure spikes than the Joukowsky predicts. You will have a wave travel down it, and when it hits the dead end, it will actually reflect positively. So you can almost get double your Joukowsky pressure from a dead end. Typically, those are worse with what I would call square wave behavior if you're looking at your pressure profile animation. If the wave front is steeper, your dead ends are going to be more significant. They're going to cause more issues. And then multiple pressure surge sources. If you have a valve closing here and a valve closing somewhere else in the system, those will interfere. They will add and subtract. They might cause cavitation. So when you have complex systems, the only choice you have really is to model it in a computer simulation using a tool like AFD Impulse. And one of the final things is line pack. Line pack is essentially frictional resistance to flow generates line packing, which is a sustained pressure rise in the pipeline behind the Waterhammer wavefront after the closure of a discharge valve. So that's a kind of a specific situation. This is from Lou's paper in 2016. It's ASME paper. There's actually a application example in there that we use in our verification cases, and I use it as an example in this webinar as well. Very, very good paper. I recommend reading it. There's a lot of ambiguity and disinformation out there about line pack, what causes it. what it means, how to calculate it. Read that paper. Lou can explain it better than me. Okay. So first example is looking at Joukowsky. We have 4 different cases. They're all going to have the same initial flow, fluid, valve closure, and overall length. Various piping arrangement changes have been made to represent simplified but typical real arrangements. I list out the initial velocity and the initial wave speed there, show the Joukowsky equation, and calculate the delta P. So all of our friends across the pond might not have to deal with these conversion factors to get everything to PSI, but here in America we do, so that's what all this pretty stuff is on the tail end. But we can look at this. All of these are 12-inch pipelines that are 4,000 feet long. I think I had this at 2,500 gallons per minute. I close this valve instantly. We have a pipe expansion and then contraction. So we have this partial area that has a larger diameter. We have a flow split, still both 12 inches. Whoops, where did we go? And down here we have a dead end, just 250 feet long. So let's see what happens when we close that valve at 1 second. In the simulation, I closed all of the valves at the same time at 1 second. We can see that the initial delta P is exactly the Joukowsky pressure rise, okay? But that's the red line. So that will oscillate back and forth given the kind of the typical Waterhammer example, single valve reservoir, instantaneous closure. There's a good example of that in the impulse help file where you can see all of the behaviors at each interval of L over A. But what we're seeing here is that at the diameter change, we see some partial reflections, and oh, that spike's bigger than Joukowsky. It comes back and it has this funky oscillating behavior. Parallel lines are kind of similar but a little different. And then the worst is, and the most noise generating, is this dead end. And you can see as that keeps going, we actually get a delta P from our initial pressure of 724 PSI when we have a dead end and an instantaneous valve closure than if we just have a straight pipe in his single instantaneous valve closure. So that's a difference of, let's see, like 330 PSI. That's barely significant. That's extremely significant. I used Impulse's visual report animation to do this. So we're going to actually look at the pressure at each node over time during this event that I just showed there. Before, we were just looking at the pressure at the valve. We're going to look at it throughout the system. We're going to be able to see partial reflections at these T's. That's going to be important. So see what happens at these T's. See what happens at these diameter changes versus the simple behavior that happens in the straight pipe, okay? So you can look at the time. Nothing's happening until 1 second. Boom, okay. You see lots of partial reflections. And then pay close attention to right around here, around 6.5 seconds. That's when we saw the highest pressure spike. Boom, okay. So you can see there's a lot more noise happening on this dead end one than the other ones. But you can see partial reflections coming at the area change, partial reflections and flow splits at the parallel lines. So all of that's very important. Okay, so we looked at kind of system arrangements. What happens with cavitation? This example's from Wiley and Streeter, page 195. And I'll have all the references at the end of the presentation, so you can actually look at the additions and everything. So this is a really short system compared to the other ones we've been seeing, 36 meter long, 19.05 millimeter inner diameter copper tubing. So this is kind of your academic test case. We're going to close a ball valve suddenly. The initial velocity is 0.332 meters per second. Wave speed is given by the example, and we can actually calculate the head change. And this was an experiment that they actually carried out and measured data for, and we compared that to impulse, and it matches up really well actually. For more information, check out the verification files. This is impulse verification case 4. So if we have a sudden valve closure, we can see that results in the Joukowsky pressure. So we have this initial pressure rise, great, but then it reflects negatively after that pipe, that surge communicates back upstream, downstream to the valve, and then it pulls the cavity. So that's what we're seeing here. It's actually a fairly linear cavity generation. You can see I've plotted the vapor volume on the secondary y-axis here in milliliters. It's a very small amount of volume, but remember we have a pretty small pipe. So we have pretty linear vapor cavity generation, and then a sudden collapse. We get a spike, and then there's another spike that actually takes the pressure significantly higher than the initial spike. So we had Joukowsky estimated a DH of 43.32 meters. Using impulse, looking at cavitation, this is a delta H of 86.42. So almost exactly double what Joukowsky would have predicted. And you can see there's still some higher than Joukowsky pressure spikes afterwards. Let's keep going. Yeah, and I think based on their measured data, their measured pressure spike was close to 100 meters, or head spike. We're talking about head. In this case, a lot of the academic papers, a lot of reference materials use head instead of pressure. Was about 100, so this is 110. Okay. Line pack example. This is from Lou's paper, Jim Lou. I've attended a couple of his courses. I've met him in France at a pressure surge conference. Good guy. This is an 80-kilometer long crude pipeline. We're looking at a 60-second ball valve closure. There's a full poured ball valve, or 180-second closure, full poured ball valve. In the example, both closures start 20 seconds into the simulation. The communication time or pipeline period is 139 seconds. So you would think the 180-second ball valve closure might not exhibit a rapid event. We'll talk a little bit more about that later, but anything that's longer than your pipeline period can be considered a quote unquote slow event. But we'll see why this might not be the case when we look at the next slide. And then once again, I calculate the Joukowsky head rise. It's calculated to be 213.24 meters. We have our wave speed, our velocity change. And if anybody's wondering why we have these negative values, so if we have V2, let's look at H2 minus H1, then we have to have V2 minus V1. Well, V1 is our positive initial velocity, and our V2 is 0, so that's why V2 0 is negative, and that counteracts this other negative, so we get a positive head rise. So that just keeps track of that for the deltas, making sure that the deltas stay intact. And this is also in our verification cases, imp verify 22. So essentially both closures are effectively instantaneous even though the 180-second closure is greater than 139 seconds. You can see there really isn't much pressure change until the final 40 seconds or so of closure. There's a little bit before 40 seconds. So if we're closing at 20, the final 40 seconds are 160 to 200. That's where all of the pressure rise is happening. That's faster than your pipeline communication time. So it's effectively instantaneous. We're looking at a DH of 213.24 would be the Joukowsky head rise. But we're actually seeing 228.8 meters for the 60-second valve closure, or 254 for the 180-second valve closure. Well, what's happening is we're actually seeing some line pack as the valve is closing. It just doesn't happen after the valve is closed. There's still that line pack. There's still some frictional recovery. Just essentially the simplest way to refer to what line pack is during the closure. And then you can see after the valve is fully closed, we kind of have this slope change. There's this almost discontinuity. And from here to this point, we see that is line pack. That's what's happening. We're getting some head loss recovery at the valve. That's really kind of what's happening there. And we see that the DH in that case is actually 540.9 meters. That is more than double what was predicted by Joukowsky. And if we look at the 180-second closure, it's 533.1, all negligibly different. We could have modeled this with an instant closure and basically seen the same thing. But all of this is highly system dependent. All of this is communication time dependent. All of this is valve dependent, your fluid. And then this is really going to depend on what happens upstream as well. This is kind of a simplified test case where it's just a reservoir upstream. If you have a pump upstream, it's going to behave differently. So in cases like this, it's going to be important to model what your pump is actually doing. If your pump's going to trip in any event like this, if your pump's going to deadhead. If your pump's going to deadhead, we probably actually see a worse response in this because you get line pack plus your pump curve being pulled back to its zero flow position and generating more head on top of that. So considering those things is really important in this when you're modeling line pack, cross-country pipelines, things like that. Okay. Quick note about line pack, it happens in all systems with friction, but the effect is far more pronounced in long systems with viscous fluids and significant pressure drop. The nice thing is AFT Impulse solves line pack without having to alter any settings. If you put in your absolute roughnesses right, if you put in your viscosity right, you put in your fluid, all of this is solved by accurately solving the fundamental equations for isothermal flow of a liquid. So there's the conservation of mass, often referred to as, which is the continuity equation, or Newton's second law of motion, momentum equation. Those are the two equations that are solved by the method of characteristics. That's what impulse does. By solving those correctly, you solve line pack correctly. Okay, pipeline period, communication time. T sub C equals 2L over A. So L is any given pipe length. If you have a long system with multiple different pipes, you can estimate what your T sub C is. You could go pipe by pipe and calculate it, but you can kind of estimate an average wave speed and then look at your overall length. And that will give you a pretty good idea of what your T sub C is. And that will allow you to say, okay, my valve closure happens in 30 seconds. but my system is this long, my average wave speed is this. Is that valve closure effectively instantaneous? Am I going to have a chance for the upstream boundary condition to relieve the pressure rise to communicate itself back down to my closing valve that, hey, I'm still here, this is my pressure, I'm going to force that upon the system? Or does it not even have a chance? Does it not even see that pressure wave before that time? That's going to be a critical thing. And then looking at your valve closure after you've done that is look at the flow and pressure rise change at the valve. If you have a very large valve, a full bore ball valve, a full bore gate valve that is the size of the line, it's not really going to restrict the flow until the final few percentages of closure. So you might still have, in effect, an instantaneous closure. That's going to be really important. If you want to learn more about ball valves, gate valves, inherent characteristics, check out my other webinar we did about the importance of inherent valve characteristics in Waterhammer analysis. I gave that maybe a month ago or so. Look in our archive, see that's a good webinar. So we were talking all about effectively instantaneous. Any real valve closure is not effectively instantaneous, especially if you have a complex system. The wave is going to interact with components along the line before the upstream boundary condition. So if we redid our dead end valve closure case, still had a closure faster than 2L over A, we'd still have an effectively instantaneous closure, but we wouldn't see the same pressure rise because it wouldn't interact with that dead end the same way as an actual instant valve closure. So when you're modeling things in impulse and you have complex systems and you say, I don't know exactly what my valve's going to do, I'm just going to make it an instant closure. Just be aware that that's going to probably make your interactions with dead ends, flow splits, and other things before you get to your upstream boundary condition more aggressive than they would be in real life. So keep that in mind. And that means it's kind of imperative to model a realistic valve closure profile or a pump trip if sizing surge mitigation components, such as relief valves or accumulators. If you have a really long line and a sudden valve closure, say like you're doing a loading arm case, you have an emergency release coupling, getting that valve closure profile and that time accurate is going to change how your relief valve responds. Your relief valve might not be at your upstream boundary condition because that's a terrible place for it. You want your relief valve as close to the source of your surge as possible. So if it's right there, you can think of it as a different communication time. Your T sub C is going to be the length from your valve to your relief valve. That's going to start to matter, okay? So if those are actually really close, your T sub C is going to be pretty small, maybe in the order of milliseconds. So getting your valve closure accurate is going to matter for those. Let's talk about magnitude and the rate of flow change. So whenever you start a surge analysis, think about how much does my velocity need to change? Higher initial velocities will typically result in a higher pressure rise. How fast are you going to change it? Faster rates will typically have higher pressure rise. So those kind of go hand in hand. You can think of, you can have actually a very small pressure rise even starting with a high initial velocity. You just have to have a very long rate of change. And that rate of change, if you have a constant rate of flow change, which isn't quite realistic, but if you have a constant rate of flow change, that's going to be constantly adding a certain amount of pressure onto your system. So you have to extend that pretty long. longer than your communication time, and get that ideal pressure rise. So, and you can think of that, that's kind of, this indicates there's really two primary ways to directly mitigate surge, having a lower initial velocity. And no one likes to hear that, but that's really the case, is a lower initial velocity and a lower rate of velocity change is all at the core of this. That's what relief valves do. That's what surge accumulators do, is they lower the rate of velocity change. But that's not what you typically think about, but that's at the basic physical level what they're doing. They give an alternate flow path for the velocity to go to, rather than through a closed valve. They're able to go elsewhere, and that changes the rate of velocity change. That lowers your pressure response. Okay, and then when you're thinking about this, think about the whole system, not just a point. What is my velocity change at the point? But your whole system is going to interact. How you shut down everything is going to interact and change your pressure response. Okay, and then I have this interesting example. It's actually possible to have a higher pressure rise when using a longer valve closure in complex multi-valve systems. So here's a quick example. Higher pressure with longer valve closures. So I kind of already gave it away, but this is an LNG loading system. There's multiple valve closures in series during an emergency shutdown event, that's ESD. All of the valves that are triggered to close on an ESD event close simultaneously at 25 seconds into the simulation. So you can think of that at t equals 25, all of my valves are closed, or one of your valves can be extended to 30 seconds. What would be the worst case? Let's see. Here's a response at an emergency release coupling in that system where all of the valves close at 25 seconds. We see our pressure gets up to about 16 bar, which is close to 16 atmospheres, or 225-ish psi. This is the pressure response when we close one of those valves in 30 seconds. It's not too much. It's 1.34 bar higher, almost up to 18 bar, 17.5 bar. And why that's happening is because your flow is going to be stopped in 25 seconds either way. There's really no reason to extend a valve closure to 30 seconds if all of your valves are closing in 25 seconds. And this depends on your systems. It depends on how far apart each of your valves are from each other. But this is a fairly short-ish system. So 5 seconds is enough time to make a difference. And if one of those valves was a little more closed in sync with the other ones, it would have helped slow down the momentum as a whole system and lower the overall pressure rise. So little changes like that can matter. That 1.34 bar might be the difference between a system's pressure rating or not. Maybe you have a flange that's rated to 250 psig or 17 bar, and you can't go above it, and that's what you have to stop at. And it's just that little thing is critical, so keep that in mind. Okay, forces, here we go. Forces are different. They require a different thought process for a surge analysis as compared to when you're only looking at pressures. Forces are highly dependent on the waveform of the surge, the steepness of your wavefront. When you're looking at animations, it's so helpful whenever you're like analyzing forces. I mean, it's extremely helpful when analyzing pressure surges, but for forces, it's critical. So it's not dependent on absolute pressure, but pressure difference between nodes. So we're looking not at a force at an area, unless you're maybe discharging to atmosphere, that's a different case. But if you're looking in between pipe nodes, pipe force sets, it's all about pressure difference between nodes. You have a force over an area and a pressure over an area is a force compared to the other pressure over an area. That's dP, not absolute P. Okay, it's your differential pressure that matters. In this system, they're all the same. And then once again, we have different valve closures. I have so many little random valve closure test cases I've built up over the years. So I just kind of grab them and put them in here. But this one I like a lot. I look at a 1 millisecond valve closure. And then I thought it was really interesting to consider valve closures at different intervals of L over A to really show how critical communication time is in a system. So 1 millisecond is essentially instantaneous. You still have to have some sort of time closure and impulse, so 1 millisecond it is. And then you can see my second values for L over A, 2L over A, 3L over A, and 4L over A. And I calculate what my Joukowsky pressure rise is going to be at 542.57 psig. So had to be real specific there. Here's the pressure response. I made it so all of those valves, even though they have different closure times, the time when they finish closing, where the open percent of the valve is 0, is all 10 seconds. So I backtracked it. Some of the valves start closing earlier, like so the 4L over A valve starts closing at 10 seconds minus 4L over A, and same going forward. So you can see that the maximum pressure, all of my maximum pressures happen at exactly 10 seconds. You can see these are actually relatively similar. I mean, there might be a couple hundred PSI difference, but you can see everything that's 2L over A or shorter essentially has the same pressure rise. This is a shorter system, but you can actually see this little bit of slope. And this is a water system with not much pressure drop. And you can see there is actually a little bit of line pack, but it's more obvious in the crude oil pipelines. But let's look at the forces. So I looked at a force set. I defined it from going back to the overview. Essentially, each of these final pipes is a force set. So that's 250 feet. So I did, this is my node 1 is the inlet of pipe 4, and my final node is the outlet of pipe 4. So we're going to be looking at the force caused from unequal pressures caused by surge in pipe 4. And same with 34, 40, 44, 54, and 64. That's where all of my force sets are. So you can see, even though my pressure, my maximum pressure is almost the same for my 1 millisecond, my L over A, and my 2L over A case, just going from 1 millisecond to an L over A closure time cuts my pressure spike almost in half. We're at, I don't know, let's see, 27,000 pounds force down to 15,000 pounds force. And it's even more dramatic down here. This 4L over A valve closure has a pretty mild force response for closing in less than a second. Okay, so that's critical when analyzing forces. Okay, so let's look at this animation. I'm starting at 9.2 seconds. Nothing's really happening before then. Let's see. Everything's going to be interesting when we hit 10 seconds. So we're at 9.5, 9.6. You can see the pressure rise is increasing for the slower valve closure cases. Boom. Right at 10 seconds, you can see this. We're a little bit past 10 seconds. You can see this very sharp wave front for this instantaneous valve closure. So you can think about what's the pressure up in the corner compared to right at 750 feet. Okay, so let's watch this go forward a little bit. You can see, yeah, my faster closure times do have steeper wavefronts. You can see the second steepest wavefront is L over A, but it does not compare to that instantaneous wavefront. Okay. My next slide, I just paused it at 10 seconds and took a screenshot. So this is going to be what our maximum forces are. You can see, okay, so in my stagnation pressure, so 1 millisecond, we have essentially our Joukowsky pressure down to our steady state pressure. That's quite a large force difference. Let's see. Let's do a pen. So we have this node to that node. That's quite significant compared to this. Let's see, our shallowest 4L over A here. I mean, look at that line. If you think about that slope of that line compared to the slope of this line, they're very different. Much steeper wavefront, and I mean, this wavefront's actually this steep. I mean, that's crazy. It's a very significant difference, okay? So that's why we're seeing very, very, very different forces with maybe somewhat similar pressure response. Okay, let's talk about typical worst case events. These are oftentimes events outside of your control. So maybe you've only been doing surge analysis, thinking about, this is something I have complete control over. This is what my valve closure is going to be. This is what my controlled pump shutdown is going to be, because I programmed that way, because I'm a good engineer. Your system has different plans. You can lose power to everything. If that happens, your control pump shutdown's not happening unless you have a giant battery bank. Those are really expensive. Those are really large, not really a practical solution. Okay, so typically pumps stop providing flow, stop rotating. Well, they might continue to rotate, but not have any flow. But the flow will probably stop in 1 to 10 seconds following the trip. So try to model that accurately. Use impulse. Trip all of your pumps at once based on inertia. See what happens. Probably might not be the best response. You might not be happy with it. You might need a surge accumulator. You might need a vessel. You might need a surge tank. You might need a giant flywheel on your pumps to keep it spinning. If you lose all of your power, there's lots of different solutions for that. But it's a very real possibility. It might happen. Loading valves on ships. The people on the ship, they care about the ship, not your system. Something's happening, something bad's happening, they're going to close those valves as fast as possible. Are those valves going to close faster on the ship than they are on your piping system, especially for loading docks? It's really important. Emergency shutdown. Do you have specific regulations for a fast closure time to prevent leakage, to prevent spillage? If you do, you're kind of working within a fixed timeline. You can't maybe say, well, this would have a better response if we just extended our valve closure. Sometimes that's not an option. You have to do something different. You have to do a different valve size. If you choose a smaller valve, you might be able to start controlling your flow sooner. If you choose a different valve type, you might be able to start controlling your flow sooner. You might be able to vary the actuation of your valve. Close it really quick and then slow down your closure right before you're done closing. That oftentimes referred to as the 80-20 closure profile. That's not a hard and fast rule. We're gonna have to test it, but typically that's kind of saying, I'm gonna close my valve 80% of the way in the first 20% of closure time, and then in the remaining 80% of closure time, I'm gonna close it the rest of that 20%. And so that really extends out the last little bit of closure where maybe even large valves can throttle flow. but that depends. If you have really, really large valves, you might need to do something even different than that. You might need to change your throttling rate, and you might not be able to close it 80% of the way in the first 20% of time. You might not have an actuator that's powerful enough. You might not have a motor out there that's powerful enough. So you have to be creative with that. Things you might be able to do multiple valves in parallel, close one valve fast, leave one valve open, maybe a smaller valve, and close that slowly. Powered emergency release couplings. These are really cool. They are essentially kind of like quick disconnects, especially for loading arms. These things will cause surge. They close typically less than 3 seconds. They will generally require some surge mitigation device. So determining the valve CV profile of that release coupling is extremely important. Typically, they're 2 ball valves in series with like a flange between it that they close and then break off, and they try to get 0 spillage. Really interesting devices. Check them out. Email me if you want to learn more about those, or I've got a collection of videos I really like for those. Okay, so complications that occur in multi-fluid systems, multi-component systems. Okay, this happens especially maybe in like crude oil terminals, things that handle heavier and lighter crudes. This is where determining your worst case scenario is quite difficult, because typically the densest fluid with the highest bulk modulus, and that's typically the same, not always, will have the worst response. However, that might not be true for systems that have highly different operating points for fluids due to changes in density, flow, viscosity. And that viscosity can be pretty important, especially for crudes. Your heavier crudes are going to be very viscous. And your operating point for your pumps, your operating pressure might be a lot higher. Your relief valve set points might need to be higher for that type of fluid. So you say, I've done this. I looked at my densest crude and I determined all of my set points that I can, this is when I turn off my pump because that's going to protect the system. This is when I open my relief valve because that's going to protect the system. And then you put a completely different type of fluid in that system. A light crude, it will not behave the same. It's going to have a different pressure response. It's going to require maybe a much lower maybe operating point on your pump. And so as your transient is happening, it might not hit that set point until it's too late, until your transient's over, some sort of fast event happened. Maybe it didn't pop your relief valve because it had a higher pressure difference to go up before it popped that relief valve. And that pressure difference is kind of important. How soon that valve opens is kind of important. How soon your pump trips is very important. So when you're looking at multi-fluid systems, should at least run a few test cases of each fluid. And maybe when you're finally done, kind of double check that your surge mitigation strategy works for every fluid type that you think is going to come through that system, or at least maybe your most viscous, densest compared to your lightest, least viscous systems. Kind of create a bracket. That might be the best you can do because who knows what's going to go through that system. That's where engineering judgment comes in. You have to kind of make a judgment call. What's going to actually happen here? Okay, reservoir levels in pumping systems is also kind of important. You can think of this like, okay, well, I have a tank and then it can be empty or full or somewhere in between. Somewhere in between might be kind of boring. Maybe nothing happens there. But you can think of high tank levels could potentially provide higher initial system pressures. Yeah, that's true. maybe you'll be more likely to overpressurize your system on a valve closure if your initial pressure is higher. That makes sense. However, low tank levels will have a lower initial pressure by that hydrostatic pressure difference, but it can be worse. Okay, lower pressures mean you're more likely to have cavitation or liquid column separation on a pump trip, or more significant liquid column separation than before. Pumps, in order to create that same flow, they're gonna maybe have less help from the upstream reservoir's hydrostatic pressure. They're gonna need to have higher hydraulic torque across it, and they're gonna trip faster. That means your flow is gonna stop faster. That could be worse. In cases where the fluid may be significantly high, you can actually have fluid continue to flow through the pump after the pump's tripped, and that depends heavily on your reservoir, that depends heavily on your system, but you can have a reservoir level high enough, tank level, maybe a reservoir is not the right word, because you could think of most reservoirs probably don't have too much of a level change, a little bit, depends on if there's a drought, but when your pump trips, you have a high reservoir level. You can have continuous flow through your pump. What does that continuous flow mean? That means you have smaller velocity change. You have smaller velocity change, you have a milder pressure response, okay? And so keep that in mind. All of this is heavily, heavily, heavily dependent on your system, your fluid, your tank, and pump, okay? So definitely run a couple test cases before determining what is your worst case. Okay, so complications with relief systems. Opening the relief valve sooner or at a lower set point can help alleviate surge. It can result in overfill or the valve failing to reseat after the initial surge has been mitigated. So I've seen that before is, oh, well, I need a little more margin of safety for this relief valve. I need it to open sooner so that my pressure doesn't get any higher. This has to be sized pretty dang specifically. Your relief valve CV or orifice needs to be the proper size for what flow is going through it. But if you open a valve sooner, that pressure might not drop back down below that pressure. That valve might just stay open. That can be pretty bad for systems, especially if that relief valve is leading to a gas accumulator that can maybe overfill it, over compress the gas. And I've seen systems where the initial surge is mitigated by opening the relief valve, but then that increased flow into their surge tank actually overcompresses the gas, overpressurizes that relief line, and that communicates back into the main system. So keep that in mind with relief systems. So yeah, for these types of cases, sometimes you just have to run a lot of cases. So final thoughts are, when in doubt, run the case. Make use of Scenario Manager. It is there to help. It really isn't that difficult to make multiple scenarios, multiple scenario trees. If you look about it logically, if you lay out a plan of what cases you're going to look at before you run them all, you can kind of lay out your basic system and then create this whole tree where you look at different fluid types, different valve closures, different arrangements, different set points, and run all of them. And once you have your base system down, that's the hardest thing to get together, is getting your basic system laid out. Once you have that done, adding more cases sometimes isn't the most difficult thing to do. Another thought is, your current worst case might not be the future worst case. What is going to happen in the future? Are you going to expand? Is another system going to get tied in? Are you going to get more demand? Say we need to increase our flow rate because we're going to make more money if we do. What's going to happen in that case? Maybe you can't buy the equipment now because that's future to mitigate it. But maybe you can plan on maybe adding a T at some point with a flange on it where you can say, okay, this is where we're going to connect future surge mitigation equipment if we need it at minimal capital cost right now. Okay. Think of a system as a whole rather than just a single valve or a single pump. What are all of the components going to do during a transient? What would cause your system to have the most dramatic change in flow in the least amount of time? And then finally, ask an expert. That's us at PMTG and AFT. And that's it today. I went over a little bit of an hour. I had a lot to get through. Hopefully you guys enjoyed it. I'll go back up to my title slide and let's see, let's have Ben take over.
Awesome. Dylan, thank you very much. That was an outstanding presentation, and I hope all of you enjoy it. Bottom line is, everybody, you need to be doing a Waterhammer analysis. If you're not doing Waterhammer analysis, you need to be. And the ASME B31.3 and B31.4 actually advise that you do look at Waterhammer. It's required by the codes. And to also evaluate the stress levels in the piping system. And if you're not looking at Waterhammer, it is opening up so many opportunities for things to go very badly in the system, and it's really important to try and avoid those disasters of Waterhammer problems. And when you use AFT Impulse for the scenario manager and the graphing capabilities, it makes it a lot easier to really get a strong understanding of what's going on in your system. That way you can use it to help clearly explain to your operators, this is why it's so important to close these valves in these ways, or this is why it's important that we have various surge suppression equipment in place, and why it's important that things are sized properly rather than just sticking things in the system and hoping it works. So if any of you do not already have access to AFT Impulse and you want to try it out, you can download free demos on our website. And the demos are intentionally limited versions of the software meant to simply give a look and feel of the interface. And there's 3 different options for the demos that you can work with. You could switch between any demo at any option at any time. But if you want something better, you're welcome to use a evaluation license of our software. That's the full version for free for a limited period of time. And that way you can try it out for yourself and see how it can work for your systems. Anyway, thank you again, everyone, for your time and listening in. If you have any questions, please feel free to let either Dylan know at his email address on the slide, or you can feel free to contact me as well at benkeiser@aft.com. That's BENKEISER@aft.com. And take care, and we hope that you all have a wonderful rest of your week.